So let us continue with sequences LAQ. This is the most important LAQ. Show that every sequence Sn has a monotonic subsequence. So let us see, how do we begin? Consider a sequence Sm and assume nth term be the greatest term. Such that Sm is less than Sn for all m greater than n. Now we consider a subsequence. We denote that subsequence with S and K. For the sequence Sn as Sn1, Sn2, Sn3, so on up to Snk minus 1, Snk, Snk plus 1, so on. Okay. So here we get two cases. Case 1 is if there are infinitely many greatest terms. If there are infinitely many greatest terms, then we consider Snk as a decreasing sequence. So how do we mathematically denote a decreasing sequence? That is Snk plus 1 is less than Snk for all k. This is case 1. Now what is case 2? If there are finitely many greatest terms, then select n1 as greatest term. Select n1 as greatest term in the sequence. That is capital N greater than or equal to n1. There exist, this symbol means there exist m greater than n, then Sm greater than or equal to Sn. This is equation number 1. Now if n is equal to n1, then n2 is greater than n1, which implies Sn2 is greater than or equal to Sn1. This is equation number 2. Now if n1, n2, so on up to nk have been selected such that n1 is less than n2, n2 is less than n3, n3 is less than n4, like that up to nk. And the corresponding subsequences are also in order, like Sn1 less than or equal to Sn2 less than or equal to so on up to Snk. So n is equal to nk gives nk plus 1 greater than nk, such that Snk plus 1 greater than or equal to Snk. So by mathematical induction, what can we say? Snk is a non-decreasing subsequence. If it has a non-decreasing subsequence, that means it is monotonic. Understood? Now let us take the next question. This is also very, very important. State and prove Bolzano-Weierstrass theorem. Either they can ask this way directly, or they will ask, prove that every bounded sequence has a convergent subsequence. That also means that they are asking you for Bolzano-Weierstrass theorem. So let's see how to prove. First, let us write the statement. If they ask you state and prove Bolzano-Weierstrass theorem, then first write the statement. So this theorem states that every bounded sequence has a convergent subsequence. Okay, so let us start with the proof now. Let Sn be the bounded sequence. As every sequence has a monotonic subsequence, like in the last theorem we have proved that every sequence has a monotonic subsequence, then let us say S and K. Subsequences we always denote this way. Let S and K be the monotonic subsequence of Sn. That is, Snk is the bounded increasing sequence. Now, as Snk is bounded, how can you write? Mathematically, how can you write the statement? So let us say U belongs to R and U is the supremum of S. Where what is S? S is equal to Sn such that n belongs to n. Now for any epsilon greater than 0, there exists capital N such that Sn is greater than U minus epsilon. Now for all n greater than or equal to n, Sn greater than or equal to Snk. Why? Since Sn is increasing. When it is increasing, we put greater than or equal to symbol. Now for all n, mod Sn minus u is less than epsilon and limit Sn is equal to u, which implies limit Sn is equal to u. Now if the sequence Sn converges, then every subsequence converges to the same limit. If any sequence converges, then every subsequence of that sequence converges to the same limit. What does that mean? That is limit k tends to infinity, Snk is equal to u. So therefore you can say monotonic sequence also converges. Monotonic sequence also converges. Therefore, the bounded sequence Sn has a convergent subsequence. That is Snk. Now take the next question, very important, state and prove ratio test. So this ratio test is nothing but D'Alembert's test. or you can also call it as ratio test. So first let me write the statement. Let's see what this ratio test states. So if sigma un is a series, always series is denoted by this symbol sigma. If it is a series of positive terms such that limit un plus 1 by un is equal to L, then a bit sigma un converges if L is less than 1. B bit sigma un diverges if L is greater than 1. C bit the test fails to decide the nature of the series if L is equal to 1. This is the statement of ratio test. Now we will start the proof. Let sigma un is a series of positive terms, that is un is greater than 0 for all n, which implies un plus 1 is also positive for all n. Now if we divide them, un plus 1 by un, that is also positive. If un is positive, un plus 1 is positive, then their ratio is also positive, right? So that means we have taken this as L in the statement. So L is positive. Let's say this is equation number 1. Also, limit n tends to infinity, un plus 1 by un is equal to L. Then, from the definition of limit, what is the definition of limit? For each epsilon greater than 0, there exists a positive integer. There exists a positive integer m such that mod Sn minus L is less than epsilon for all n greater than or equal to m. That means mod Sn minus L is less than epsilon for all n greater than or equal to m. What is Sn? Sn is un plus 1 by un minus L less than or equal to epsilon for all n greater than or equal to m. So whenever modulus is less than epsilon, we can write it as minus epsilon less than un plus 1 by un minus L less than epsilon. To remove the modulus, we can take between negative value and positive value for all n greater than or equal to m. Now what I will do is add L on both sides. Why? So that we can cancel out this middle minus L. So you will get L minus epsilon less than un plus 1 by un minus L was there already. Now we are adding plus L. So on the three sides we are adding L for all n greater than or equal to m. That means now here positive L and negative L get cancelled. L minus epsilon less than un plus 1 by un less than L plus epsilon for all n greater than or equal to m. This is equation number 2. Now we have to consider a few cases. So let us say the following. cases are considered. So here it is case 1. Case 1 is if L is less than 1. Let us say epsilon is greater than 0. Now choose lambda is equal to 1 plus epsilon such that lambda is less than 1. That means L plus epsilon is less than 1. So L is less than L plus epsilon less than L less than 1. So you can say L is less than lambda less than 1. Or we can say 0 less than L less than lambda less than 1. That means lambda lies in between 0 and 1. Take this as equation number 3. Now from equation number 2, un plus 1 by un is less than L plus epsilon for all n greater than or equal to m, which implies un plus 1. Now I am multiplying un on both sides to cancel this by un. Okay. So un into L plus epsilon, where n is equal to m, m plus 1, m plus 2, so on. And un plus 1 is less than un into lambda. This bracket I am taking it as lambda, where n is equal to m, m plus 1, m plus 2, so on. Then um plus 1 is less than lambda, and plus 2 is less than plus 1 lambda, and this is less than lambda, where lambda is equal to lambda square. Now which implies plus 2 is less than lambda square. So plus 3 is less than plus 2 into lambda, which is less than lambda square minus lambda, which is equal to lambda cube. So plus 3 is less than into lambda cube. Now if we add these above equations, what do you get if you add them? Plus 1 plus plus 2 plus plus 3 plus so on is less than lambda plus lambda square plus lambda cube plus so on. So that means sigma n is equal to m plus 1 to infinity. Un is less than into, if I take common, lambda plus lambda square plus lambda cube plus so on. That means sigma n is equal to m plus 1 to infinity. Un is less than into, these are all sum of lambda square, lambda powers. So you can write sigma n is equal to 1 to infinity lambda power n. This is equation number 4. So it is in what form? It is of the form un less than kvn. So you can see in the RHS of equation number 4, I'll go back to equation number 4. You just see the RHS of equation number 4. So what do you have? Sigma n is equal to 1 to infinity. Lambda power n is a geometric series. And 0 less than lambda less than 1. Therefore, from geometric series, sigma n is equal to 1 to infinity, lambda power n is convergent. Therefore, from comparison test, of type 1, sigma n is equal to m plus 1 to infinity, lambda power n is also convergent. Therefore, the series sigma un is also convergent if L is less than 1. This is case 1. Now we have case 2. What is case 2? If L is greater than 1. Now let us say epsilon is greater than 0. Now we will choose lambda is equal to L minus epsilon such that lambda is greater than 1. That means L minus epsilon is equal to 1. Since L is greater than L minus epsilon is greater than 1, so you can write L is greater than lambda. In the place of L minus epsilon, we are writing lambda. So you can say lambda is greater than 1. This is equation number 5. Now if you see equation number 2, you will have L minus epsilon less than un plus 1 by un for all n greater than or equal to m. I have written this. Okay. So what do you get from here? Un plus 1 by un is greater than L minus epsilon for all n greater than or equal to m. So un plus 1 by un is greater than lambda. We are taking L minus epsilon as lambda for all n greater than or equal to m. So that means un plus 1 greater than un into lambda for all n is equal to m, m plus 1, so on. We have taken this same way in the last case also. So that means un plus 1 is greater than um into lambda. So Lm plus 2 is greater than Lm plus 1 into lambda, which is greater than Lm into lambda. That is nothing but Lm into lambda square. So that means um plus 2 is greater than lambda square. Now the same way we will take plus 3. Plus 3 is greater than plus 2 into lambda, and this is greater than into lambda square into lambda. Okay, so that is lambda cube. So you can say plus 3 is greater than lambda cube. Now again, if I add these equations, adding the above equations, what do you get? Plus 1 plus plus 2 plus plus 3 plus so on greater than lambda plus lambda square plus lambda cube plus so on, which implies sigma n is equal to m plus 1 to infinity un greater than if I take common, lambda plus lambda square plus lambda cube plus so on you will get. So that is nothing but sigma n is equal to m plus 1 to infinity un greater than sigma n is equal to 1 plus infinity lambda power n. This is equation number 6. Now it is in what form? It is of the form un greater than kvn. So now if you see the RHS of equation number 6, RHS of equation number 6, you will find sigma n is equal to 1 to infinity lambda power n. That is a geometric series. Geometric series means second term by first term is equal to third term by second term is equal to fourth term by third term, like that you will get. And lambda is greater than 1. Therefore, from geometric series, sigma n is equal to 1 to infinity, lambda power n is divergent. So in the previous case, it was convergent. Now it is divergent. Therefore, from comparison test of type 2, sigma n is equal to m plus 1 to infinity, un is also divergent. Therefore, the series sigma un is divergent if L is greater than 1. Now let us move on to case 3. So case 3 is if L is equal to 1. So we consider the series sigma un where un is equal to 1 by n, which is divergent. Now since from P test P is equal to 1, which is less than or equal to 1. So limit n tends to infinity, un plus 1 by un is equal to limit 1 by n plus 1 by 1 by n. That is equal to limit this 1 by n, if we bring up, it will become n. By from this n plus 1, I will take n common. So we will get 1 plus 1 by n. This n and this n cancel. We will get limit 1 by 1 plus 1 by n. Now as n tends to infinity, 1 by n tends to 0. So that is equal to 1 by 1 plus 0, which is equal to 1. Now we consider a series sigma un where un is equal to 1 by n square, which is convergent. Since from P test P is equal to 2, which is greater than 1. Now we take limit n tends to infinity, un plus 1 by un, that is equal to limit n tends to infinity, 1 by n plus 1 whole square by 1 by n square. That is limit n tends to infinity. If I bring this 1 by n square up, it will come in the numerator. And from this n plus 1, I will take n common. So if I bring it outside, it will become n square. And you will get 1 plus 1 by n whole square. So that is limit n tends to infinity. N square cancel. 1 by 1 plus n whole square. That is 1 by 1 plus 0 whole square, which is equal to 1. Therefore, the sequence sigma un may converge or diverge. Therefore, the test fails. To decide the nature of the solution, if L is equal to 1. So with this, we are done with all the 3 cases.